the actual pointer. All right, I think we're good to go. So today we're joined by Asta Heinesen joining us from Lyon, who will be giving us a talk on blind analysis of cosmological data. Take it away.
Thank you, and thank you for the invitation to give a talk here at Queen Mary. It's really nice to be here. So today I will talk about blind analysis of cosmological data and how we might infer information about our universe expansion history without imposing a particular geometrical model for our universe. So I will talk about frameworks that are appropriate for analyzing data from both current surveys, but also from upcoming surveys. And I will in particular talk about what information we can expect to extract from data without making assumptions about the underlying geometry of our universe or the field equations that determine this geometry. And in relation to this, I will discuss how anisotropies in our cosmological measurements are expected to relate to the lumpiness in geometry that is present in our cosmic vicinity. And in terms of observables that probe such anisotropies, I will talk about standardizable objects and redshift signals, and I will discuss things in the end. So usually when we think about determining kinematic degrees of freedom in cosmology, and in particular the expansion of space, we think of the Hubble limiter law, or Hubble's law, which was first discovered a century ago by Lemaitre, Slipher, and Hubble, who realized this approximate proportionality law between distances and redshifts for objects in our cosmic vicinity. And such a proportionality law is indeed expected in a homogeneous and isotropic expanding universe model, as Lemaitre also pointed out at the time. And within such models, we can view the Hubble limiter law as it's written here, as simply a first order Taylor series expansion of luminosity distance in redshift, where the coefficient here is the Hubble parameter describing the expansion of space between test particles in this model universe. And at the time of Lemaitre and Slipher, a homogeneous and isotropic lowest order Taylor series expansion was indeed sufficient for analyzing data, which was sparse and covered a small proportion of our sky, and was in general associated with large systematic errors. And today we are in a better situation when it comes to cosmological data. We have large catalogs of, for instance, supernova of type 1a for determining distances. These supernova span a wide range of distances, and we also have a fair sky coverage, at least for certain subsamples within the largest supernova compilations. We have an okay sky coverage, and it means that we can think of being a bit more refined in our analysis of distances than a homogeneous and isotropic lowest order Taylor series expansion. So there are various ways of refining our analysis of distances in cosmology. We can either think of formulating distances within a model space-time that we might motivate from first principles or from complementary data, but we might also take a more model-independent approach if we don't want to assume the particularities of our universe geometry before we analyze cosmic data. And it's the latter approach that I'm interested in my research, and it's also what I will talk a bit about here. So the observables that I will talk about today are luminosity distance and redshift drift. And luminosity distance is a distance measure that's defined from the square root of the intrinsic luminosity of an astrophysical object divided by the flux as observed from that same object. And in order to measure luminosity distance in cosmology, we need objects that are standardizable in terms of their luminosity. And a popular such standard candle is that of supernova of type 1a. We are also starting to be able to use gravitational waves as promising independent distance measurements in cosmology. And I will also talk about redshift drift signals, which are changes in redshift in time of individual astrophysical sources. So this is an upcoming precision measurement that is going to be probed through various transition lines in the hydrogen atom. Okay, so before we move on to talking about how these observables look in a general geometrical setting, I'll just remind you of how one can formulate these observables when we are in the Friedmann limit of Robertson-Walker or the FLW class of universe models. These models are characterized by having exact translational and rotational invariance over spatial sections of these models. So they describe a universe where the matter and energy content can be described as a perfectly featureless fluid. And in this universe idealization, we can write down luminosity distance as a Taylor series expansion in redshift, where the first order term here is what you would know as the usual Hubble law, where the Hubble parameter provides the proportionality law between distances and redshift when we are close enough to the observer. And when we go to a higher order, we have the deceleration parameter entering. It is defined as the second time derivative of the FLW scale factor, and it comes with a minus sign by convention. When we go to higher order, we have curvature entering through the FLW curvature parameter. We also have the so-called jerk parameter entering, which is the third time derivative of the scale factor. And so on. We might go to higher order. We can do a similar series expansion for the redshift drift signal. And here I've just written the first order term because this is what I've managed to find useful expressions for in the generic geometrical case so far. And we see that this first order term in the FLW idealization is given by a product of the deceleration parameter and the Hubble parameter, and it comes with a minus sign, such that positive detections of redshift drift are signatures of an accelerating universe in the FLW models. And I should say that these results are for luminosity distance and redshift drift are purely geometrical results. So they rely only on assuming the FLW metric and assuming that we have co-moving observers in this metric, but they don't rely on any particular field theory for determining the FLW scale factor. And therefore, analysis that rely on these expressions are often referred to as FLW cosmography. And we can note some nice properties about these cosmographic expressions. So we have that the coefficients of these series expansions are independent on the direction on the observer's sky. So this is a direct consequence of the isotropy that is built into the FLW models as an assumption. And this means that basically at each order in redshift, we add one new parameter to be determined from data. So if we can motivate a truncation of the Taylor series, we have a finite number of degrees of freedom to determine from data. And this we can, in principle, do and extract information about the universe kinematics without having assumed the underlying field equations. This nice property of the cosmographic expressions here, we expect to break down for a generic universe geometry where we have breaking of homogeneity and isotropy. And it's not clear that we would be able to formulate nice cosmographic relations that are directly useful for analyzing cosmic data for the general geometrical case. But this I will show that this is in fact possible to write down very useful expressions. So the observable that I will talk about first is luminosity distance, and the details of what I'm going to present are in this paper, and it relies on important previous papers in literature by, for instance, Christian and Sachs, Ehlers, George Ellis, Chris Coxon, Obina Ume, and collaborators. And the idea now is to take the isotropic FLW cosmography for luminosity distance that we know well, and to generalize this into an arbitrary geometrical setting by mapping making an appropriate mapping of the FLW Hubble, deceleration, jerk, and curvature parameters into generalized cosmological parameters that will now vary with the point of observation, but also vary over the individual observer's sky on account of the breaking of homogeneity and isotropy in the underlying space-time description. So we can formulate how these effective cosmological parameters they look for the arbitrary geometrical setting. So here, here I assume that emitters and observers are given in a continuity, general relativistic continuity or congruence description. I've assumed that photons are traveling on no geodesics, and that Etherington's reciprocity theorem holds for relating luminosity distance to angular diameter distance. But there's we also need to assume that we indeed have a well-defined that luminosity distance is a well-defined function of redshift. That this adds some regularity requirements as well, but otherwise we've assumed nothing about the underlying space-time geometry here. And what we find in this very general case is that the parameter that takes the place of the FLW Hubble parameter is given here as the rate of change of photon energy along the photon null. So there's a sense in which we can think of the inverse energy function as being a generalized FLW scale factor on the observer's past light cone. And when we go to higher order, we see that the effective dissipation parameter can be written in terms of the derivative of this this effective Hubble parameter. When we go to third order, we have an effective curvature parameter in which there's a rigid focusing term entering, which tells us about how null rays are focusing as they approach the observer. And we also have an effective jerk parameter that's given as the second derivative of the effective Hubble parameter along the photon null ray. So this is a very compact way of writing the effective cosmological parameters that replace the FLW parameters. But
can I ask, why is it, there's no new geometrical terms that come into the jerk? So like derivatives of Ricci or something like that?
You could say that implicitly, because
second derivatives of H would then give that with it?
Yes, because H contains kinematic variables related to the emitter congruence,
but it doesn't come directly from the Christian-Sachs expansion.
No, it doesn't come directly from the Sachs optical equations. Right. This is basically the curvature term from Sachs optical equation comes in here in the curvature parameter.
Can you recover the FLRW parameters by assuming isotropy in these expressions?
Yes, so when you take the limit, you indeed recover the correct results. Yes.
Homogeneity and isotropy, though.
Yeah,
not just.
Yes. Yeah.
So this curly H, is that the whole parameter correspond to the expansion of space at all, or is it defined through this series expansion?
Yeah, so it's defined through the series expansion. It's just defined as the parameter that takes the place of the FLW Hubble parameter. But we will see that it indeed has to do with expansion. It does describe the expansion degrees of freedom of space, and so this we can. This is exactly the type of insight that we can get if we are now have expanding on these cosmological parameters in a clever way. So we can do a multiple series expansion of the effective cosmological parameters in the direction of incoming light, which I call E here. So E is just the direction on the observer's sky on which he sees a galaxy or a supernova or something else. And when we do the series expansion of the effective Hubble parameter, we find that the monopole term theta here describes the isotropized expansion of space around the observer. So this is exactly. So this is a very natural generalization of the FLW Hubble parameter. This is what the Hubble parameter is telling us about in FLW physics, how space is isotropically expanding. But now we also have anisotropic contributions going into this effective Hubble parameter. So we generically have a dipolar term which arises from the for acceleration of observers and emitters in our space-time when these are not geodesic. Typically, we will take this term to be 0 for physical observers that are not subject to external forces. But then we also have an important term here, which is a quadrupolar term that comes from the shear tensor, describing the anisotropic deformation of space. So the way that we can understand this term is that if the observer is looking along a direction where space is expanding more than the average direction on the observer sky, we expect to see an enhanced value of the inferred Hubble parameter in this direction for this particular observer. So this type of expansion is useful both for gaining physical insights of our effective Hubble parameter, but it's also useful because there's a natural truncation of the series here. So this is the exact expression that is that only goes to quadrupolar order, and it means that the effective Hubble parameter is determined by 9 degrees of freedom if you count the number of degrees of freedom going into the contributions here, and these are degrees of freedom that we might in principle determine from data if we have enough of it. Now we have 9 parameters to determine instead of 1 in the FLW case, but this we can do and extract information about these variables that in turn tells us about the kinematics of the universe around us. And similarly, we can go to higher order and do the same kind of multipolar expansion. And here we see again that the exact expressions for these higher order cosmological variables are again given by multiple series that are truncated at a finite order, and so these effective cosmological parameters as evaluated at the observer are given in terms of a finite number of degrees of freedom, which you can count and which can in principle be determined if we have enough data, and these so the multiple coefficients here are again telling us about kinematical and curvature properties of our universe neighborhood. Okay, and we can look at some, and we can look at some at how these coefficients look to get some insight into how anisotropy and inhomogeneity is entering in these effective cosmological parameters. So here we can look at the deceleration parameter. So here you see a quite complicated hierarchy of multiples that was first determined by Ume in his PhD thesis. And you see that, there's unlike the Hubble effective Hubble parameter that we might have guessed, kind of the effective deceleration parameter looks rather complicated, and you just have to do the calculation to get all of the coefficients right here. So I will just talk about some of the most important terms that enter in this hierarchy of multiples. So here, the first term in the monopolar contribution to knots is given by the derivative of the expansion rate in time. So this tells us about the local acceleration of length scales between test particles in the space-time. And this is also the only non-vanishing term in the strict FLRW limit. All other terms in this hierarchy are due to anisotropies and inhomogeneities in the space-time. And because of this hierarchy of correction terms, we see that the effective deceleration parameter as it enters in the luminosity distance cosmography is in fact not directly telling us about the deceleration of length scales between test particles in our space-time. And this has important implications for observations. Because the sign of the deceleration parameter is as it enters in the luminosity distance cosmography is exactly what leads us to conclude things about the acceleration of space and dark energy sources and so on from, for instance, supernova analysis. So this is important to keep in mind when we analyze data in a model-independent spirit. And so we, in principle, have terms here that are not constrained by any energy condition. If you apply general relativity here, and yeah, we can in principle have a negative deceleration parameter without violating any strong energy condition. So some important correction terms in this hierarchy of multiples is, for instance, this term here, which is given by the spatial gradient of the expansion rate of space. So it's telling us that if the observer is looking along a direction where space is expanding more, when we move away from the observer, we expect to see a positive contribution to the effective deceleration parameter in this particular direction on the observer's sky. And so this is an intuitive contribution that goes into the effective deceleration parameter, and it's also a contribution that we might expect to be dominant in this hierarchy of multiples. In realistic cosmological modeling, where in weak field approaches to cosmology, we typically have that even if we have physical variables such as expansion rates and density contrast and so on that might be bounded in terms of their fluctuations, we might nevertheless have that these fluctuations can have steep gradients, and it means that terms like this can be large even in a weak field setting. So we might already expect that terms that involve spatial gradients in the kinematical variables in the deceleration parameter, but also in the higher order cosmological parameters, will dominate the anisotropic features that the observer is going to see. So we might already expect that the dipole and the octopole are going to dominate the anisotropic signature for most observers in weak field cosmological modeling. Just from counting, just for seeing where the spatial gradients enter here. And this is, of course, something that we might be interested in analyzing, whether we can actually see such signatures in our own universe, in our cosmological datasets. But we might also, as a first analysis, look at this in observation, in the simulations. So this I've been doing together with Haley McPherson, where we looked at observers in realistic cosmological simulations with the Einstein toolkit simulations with cosmological initial conditions. So we took the cosmological constant to be 0 in these simulations for practical purposes, but this type of analysis can be repeated with a a non-zero cosmological constant. So the basic basic things I will show you do not are still present when we add a cosmological constant. So we can look at a fairly typical observer within this particular large-scale cosmological simulation, and we see that for this observer, the effective Hubble parameter is dominated by a quadrupole, which, if you remember, the expression for the effective Hubble parameter is exactly expected due to the shear tensor that gives rise to a quadrupolar effect. So here we really see the anisotropic expansion of space around the observer. And when we go to higher order, we have the effective deceleration parameter, and its anisotropic signature is dominated by a dipole, and you might also be able to see an octupole by I here. So this was exactly what we expected from the reasoning on the previous slide. We might also go to higher order and analyze the effective curvature and jerk parameters, and if you analyze the expressions for these in detail, you might also see that you indeed expect the anisotropic signatures here from the same kind of reasoning as for the deceleration parameter. Okay, so some comments on these results. For a general cosmological space-time setting, it is possible to write down the luminosity distance cosmography in terms of a finite number of degrees of freedom at a given truncation of the series, and this opens the door for, in principle, for fully model independent analysis of data. It allows for testing the FLRW ansatz, the validity of the FLRW ansatz on various scales, and it allows for doing model-independent constraints of kinematic and curvature variables that we are interested in knowing about in cosmology. And we also might be able to really take into account all of the cosmological features in one cosmological fit instead of correcting data beforehand for anisotropies, as is often done in Lambda-CDM-based analysis, where we first correct for peculiar velocities and so on. Here we can, in principle, fit for everything in the same cosmological fit. Yes, and we want to keep in mind that these generalizations, the generalization of the cosmography and the associated generalization of the effective of the cosmological parameters might have implications for the Hubble tension, and also in principle implications for the dark energy problem in cosmology. Currently I'm doing some investigations on how these features in the formalism that I described look for realistic observers in numerical simulations, and I do this together with Chris and other collaborators. And of course, we also want to analyze data at some points. So here I've been doing a first motivated search for anisotropies in supernova data based on this type of formalism. This I've been doing together with Antonin Bourdieu, who's a student at École Supérieure de Lyon. And we do this together with our collaborators, Hilly McPherson and Suhai Dhawan. And actually this paper is going to be on archive, I think, tomorrow or Friday.
Can I ask a question?
Yes.
about the Hubble tension thing. So I know Haley had this paper where she looked at the Hubble tension and how much this anisotropy could kind of contribute to that. And the answer was it was sort of percent level and not quite significant. So are you talking about something more than she did in that paper here, or is it a different effect, or just to clarify?
Yeah, so there are various, she was probably talking about this paper actually.
Yeah.
Okay, so there are various subtleties that go into analyzing the amplitude of the anisotropies that you see in this plot. Like you see here for this observer, you see a couple of percent deviation, even just 1%, yeah, 1 to 2% for this particular observer. And it's a couple, like I think that the maximum fluctuation, if we consider 1,000 observers in this simulation, is about 5%. But this is okay, this is at a particular scale in a particular simulation. So this is a 200 megaparsec over H scale. And when you compute the cosmographic parameters at this scale, you want to make sure that you can control the convergence of your cosmography. So you have to think about convergence radius and so on. So we want to think about at what scales this is actually what scales these cosmological parameters actually make sense, given that we truncate things at third order. So I would say, okay, so from a naive interpretation, it is not sufficient to solve the Hubble tension.
Yeah.
There are various, from a first interpretation,
Yeah.
it's not enough.
Okay.
It might add to something to the error budget, so you don't quite have a 1% detection of the. But I would say that there are subtleties if you do simulations that indeed take into account all of the hierarchy of structure also below the 200 megaparsec scale. This is a very crude, this is a very conservative simulation, because we've coarse-grained out basically. We are not considering any type of effects from structure below 200 megaparsec. So when you indeed do this, we see that we get bigger anisotropies. This is an analysis that we are doing now, where we also analyzing things with actual like ray tracing, so we can look at the individual photons.
Yeah, I know that she didn't use ray tracing in the previous thing. She was just sort of taking spheres into space-time, so I guess it was kind of prudent, as you say.
Yes. Okay. So I hope to be able to answer your question better when soon.
So follow up, Asta.
Yes.
So lots of all of the quantities you've been talking about, the shear and the local expansion rates, are defined within a neighborhood of a point.
Yes.
So the expansion between the decent.
Yes.
All curves. So if you're in a universe that has highly homogeneous structure on small scales, then all of those things will be dominated by the gravitation effects of what's nearby. So if I'm in the solar system, I'll have a very large shear based on the sun, for example. But I should
Yes.
show anything about cosmology for that possibility.
Yeah. So here, of course, we have in mind a congruence description that is relevant for cosmology. So here it's kind of so when you just do theory, you don't have to impose a scale in principle, and we could in principle imagine that we were doing things on a solar system scale. But actually at this scale, it doesn't even make sense to define a Hubble law. At the scale, your Taylor series expansion would be ill-defined in the first place.
You wouldn't compare anything like the cosmology.
Yeah, I mean, you would also simply because here we've assumed basically that the null rays are parameterized by redshift, and this parameterization breaks down once you have once you have bound structures,
Right.
then redshift is not a good parameter along your null race, so you don't have distance as a well-defined function of redshift. So here it's already an implicit assumption in this type of formalism that you're considering scales at least well beyond the largest bound
Yeah,
structures.
so you need some smoothing to make sense.
Yes, and this is what this is typically implicit in cosmological modeling. We just assume that we have a congruence description that's relevant for describing the scales that we are interested in. So here it's an underlying assumption, if you will, that there exists an appropriate cosmological congruence description, which we don't know of, but
Is that necessarily true? Do you need a smoothing scale in this?
I think so.
I mean, it only applies above a certain scale.
Like the shear, the local area that you're in.
No, but it only applies above a certain scale, but it doesn't mean that you have to smooth within that scale.
but you don't have to explicitly smooth, but that is what the
I mean, if you took, say,
that is what you have in mind. That is an implicit mathematical operation that you have in mind when we're talking about physics above a certain scale.
Is
I would say so. Like, even though it remains implicit, like all of these variables that enter here.
I mean, you could, if you took supernova locally
Yeah.
above, 100 megaparsec to 500 megaparsec, say, you could measure these variables from this in theory, but they're not necessarily smooth quantities.
There's a scale baked into your observable, right? Like your supernova, it's going to be a beam of light
Yeah.
from it traveling through the universe. That beam that you observe is only going to be what, parsecs across or something.
Astronomy AU across.
Yeah. Okay.
Yeah. But what's smoothing? What's being smoothed? It's inside that beam, right? Nothing
Well,
else.
the bit of space time that beam is probing is
Yeah. So it's like a probe that's like 1 AU in width.
So all of these quantities are defined things. So if you can define some congruence that correspond to cosmological observers, then you can infer these things, and they seem to be describing. They'll describe the property of a set of observers who have defined not with respect to their local environment geometry, but the universe in some larger sense. So I think there is some
Yes,
smoothing
there's an implicit smoothing involved, because we are never going to we're never going to describe things perfectly with a single congruence description. You will have all sorts of complicated physics on small scales, like caustics and merging of structures, and
I guess
so
there's
on.
now a length scale where you've got like a spatial derivative. There's a smoothing scale associated with that, right?
Exactly, this is what you would. This is what you also have in mind when you take a derivative. Like,
Yeah.
You have a box size in mind. Okay, but this is the difficult part. That's the interpretation of these things. I would say the best thing to look at it is that, I mean, we assume that there is a good congruence description describing our universe on the scales that we are interested in, and we don't know this congruence description, but we can, in principle, we can extract information from it by analyzing data within this type of formalism. Okay, I will also briefly talk about some similar analysis that we can do on the observations of redshift drift with the future surveys. Yeah, so as I mentioned, redshift drift is defined as the rate of change of redshift in time for individual astrophysical sources. And it has a simple expression in the Euler-W geometrical case, which generalizes nicely in when we are in the absence of exact symmetry. So in the general geometrical case here, you see that again, the Hubble parameter generalizes nicely into this effective Hubble parameter that you also saw for the luminosity distance cosmography. And this is in fact not a cosmography. This is the exact redshift drift signal. So there's no Taylor series expansion in redshift here. In addition to this, we have this additive term S, which is identically 0 in the FLW universe scenario. So it has no FLW counterpart, but you can think of it as incorporating anisotropies and inhomogeneities as they are encountered when the photon travels from the emitter to the observer. And we can analyze this term in various ways to really see how these anisotropies and inhomogeneities enter in this expression and makes the redshift drift signal depart from the FLW limits of this. I will not go so much into detail with this, but the results are in this paper. I will talk about how we can potentially use redshift drift as a direct probe of violation of the strong energy condition. This is and the reason that we could think of doing this is because in the FLW limits we have that the redshift drift signal can be written as the integral of the second time derivative of the FLW scale factor, such that positive detections of redshift drift are direct signature of the acceleration of length scales within the FLW universe, and the only way that we can get acceleration of length scales in the FLW universe is through violation of the strong energy condition. So positive detections of redshift drift tells us that we have a violation of the strong energy condition within FLW physics. And now we can ask if the same kind of reasoning holds when we are in the general geometrical setting. So we can write redshift drift in the same kind of with the same kind of integral functional here, but now the integrand takes a more complicated form. So we can write this in the same spirit as we did for the effective cosmological parameters in the luminosity distance case. Yeah, it's much in the same spirit. Things complicate a bit because now it turns out that now we have, in addition to the direction vector of the astrophysical source as an expansion variable, we now also have its gradient entering as an expansion variables in this expression for the integrand. And so this you can think of as incorporating information about the drift of the astrophysical source, the drift of the spatial direction. Okay. But apart from this, the spirit is much the same as for the luminosity distance, and these multiple coefficients here are again incorporating information about kinematic degrees of freedom and curvature degrees of freedom in the universe. And we can see, for instance, for the monopole, here we can analyze the various terms that go into this, and we see that there's a Ritchie focusing term that tells us how our observers are focusing under gravity, and this is also the only non-vanishing term in the strict FLRW limits. The other terms here are due to inhomogeneities and anisotropies in our space-time. And we see that apart from what might enter here with 4 acceleration, which will typically set to 0, the other terms here are given in terms of norms of spatial vectors and tensors, and they come with minus signs such that they always contribute negatively to the monopole term here. And this means that if we are in the geodesic case, and if we have satisfaction of the strong energy condition, then we must necessarily have a negative monopolar contribution to the redshift drift signal here. So if we can argue that the monopole is indeed dominating the signal over large distances of light propagation, so that we can ignore the higher order terms in this multiple decomposition, then we can say that if the strong energy condition is satisfied, then we must necessarily have negative redshift drift signals, and it in turn means that if we are taking a positive redshift drift signal, this is a direct signature of strong energy condition violation. So this is potentially a direct way, just from the sign of the redshift drift that we measure, to really probe the strong energy condition model independently.
About 5 minutes.
All right. Yeah, so I can also just briefly mention that it is possible to do cosmography with redshift drift. If we have low redshift measurements of redshift drift, it works much in the same way as for the luminosity distance. We can expand in redshift and see that we have a generalization here of the FLRW cosmological parameters, and there are some things that complicate the cosmography relative to what we saw for the luminosity distance. We have the position drift entering in the effective deceleration parameter of the redshift drift cosmography. This potentially complicates things, because position drift is in itself a precision measurement, just as redshift drift is. But I think I actually solved this problem now, so we don't need to worry about position drift anyway. But it's a calculation that I'm doing now, so I don't. So
When you
it's not
say
on the slides.
you don't have to worry about it.
Yeah.
I mean, stuff would drift. It just doesn't come into this.
Stuff will drift, but if we are consistently expanding things, you can also expand. So the position drift itself for a nearby source, you can expand in the affine parameter itself. And if you do this, you will get a cosmographic expression for position drift that you can plug in to this into this relation, and so you get a relation that is that can be written purely as a multiple decomposition in the direction vector E.
I see. Right.
So this is very convenient, because the direction vector is something that we just have, that we measure directly, and have access to immediately. And you can also analyze these coefficients if you will. I think I will not talk about this in so much detail. So there's a focusing term, which is the only surviving term in the FLRW limits, There are also other interesting terms, for instance, the electric part of the biotensor, which in Newtonian physics has a counterpart that is the tidal tensor, and it describes how the gravitational field strength is varying between test particles. It's varying between test particles in the Newtonian limits. Okay, and it turns out that these terms are, for instance, the dominant terms when you are considering certain LTB and Swiss cheese models. So, okay, so some comments on redshift, on these results on redshift drift. The redshift drift signal is in general modified in various non-trivial ways because of breaking of homogeneity and isotropy. And we can analyze these modifications of the signal, and because of the form of these modifying terms, it turns out that redshift drift is a promising model-independent probe of violation of the strong energy condition. And this is in fact consistent with numerical results in the literature by for instance, Sophie Coxbank, who has some nice papers on this, where it indeed seems to be hard to generate a positive redshift drift signal unless you have violation of the strong energy condition. And we actually have a paper together now. I think that Sophie put it on archive, where we are analyzing LTB models, which can then also be used to say something about Swiss cheese models. Yes, and redshift drift signals can, in principle, be analyzed with cosmography if we have enough low redshift drift measurements. This is probably a long-term future goal, but in principle, it's possible. Then we might also be interested in understanding local motion effects, for instance, within bound structures, and how they affect drift, cosmological drift effects, and how they can be distinguished from the cosmological effects that we see from differential expansion of space, for instance, which I talked about here. So this I'm looking at together with Nikolai Kosinski. We might also be interested in reducing the number of degrees of freedom that go into these cosmographic expressions for both redshift drift and also luminosity distance, in order to more realistically analyze data sets of a finite size. So this I've been looking at together with Haley McPherson on how to do this while still maintaining a lot of generality in the geometrical description.
We're past the hour now, so.
All right, I'll just I'll wrap it up. This is the final slide. So I would just like to stress that model-independent analysis of cosmological data is possible. This requires sufficient data, control over systematics in this data, and sufficient sky coverage. So this is going to be interesting for upcoming surveys of, for instance, supernova, where we're going to have access to hundreds of thousands of supernova within 10 years. We are also going to have access to completely new cosmological measurements of, for instance, cosmic drift effects. So in the reasonably near future, we are expected to have the first measurement of redshift drift with the ELT. And until then, we might do constraint analysis with available distance redshift catalogs. We might consider numerical simulations to get an idea of these effects, and to do forecasts for upcoming surveys, there's also lots of things to develop on the theory side. We are interested in formulating model-independent frameworks for more types of observables, and also to optimize the frameworks in order to make them suitable for directly applying them to blind analysis of cosmological data. So, yeah.
Very much for that. Right, we are after the hour, so I understand some people might have to leave immediately, but if you want, if there's a quick question that anyone wants to ask before we switch to the student question session.
I do have a very quick question. Thanks very much for your talk. It's really interesting. Which is about what do these quantities look like in linear cosmological perturbation theory around CDA?